Welcome everybody. In this lecture, we're going to discuss acid-base or donor acceptor chemistry. Acid-base reactions are among the most common reactions that you can encounter in chemistry. Before we discuss acid and bases in more detail, let's look at something which is common to all reactions. Now on this slide, you can see simplified reaction energy profiles of a generic reaction that converts reactants into the products. The graph in green depicts that of a normal reaction, and here you can see that the reactants have to absorb sufficient activation energy to reach the transition state, which is the maxima of this green curve, in order to react downhill to form the reaction products. The graph in red and the graph in blue are more specialized scenarios, and you don't really need to know these in more detail. We will just discuss them briefly for the sake of completeness. Now the graph in red depicts that of a catalyzed reaction. In this particular scenario, you are adding a catalyst which interferes and reacts actually with the reactants to form multiple products along the reaction pathways. Each of these smaller reactions require smaller activation energy, and overall the products can be formed with less energy. For the graph in blue, we have the scenario of a poisoned catalyst. Now, that is very similar to that of a catalyzed reaction, but along the reaction pathway, somehow a product is formed which has actually lower energy than the desired product. Now, to convert this particular product to the desired product, this would be an uphill task energetically, and so it will not really occur. So in this particular scenario, you have formed a product which is different from the desired product, and we will refer to that as a poisoned catalyst because you actually cannot get your desired product. Now what you can see here also is that the free Gibbs energy must always be negative for a reaction to occur. In other words, the combined energy of all the products must be lower than that of all the reactants. Now the free Gibbs energy has three equations that we are concerned with. The first equation relates the free Gibbs energy to the equilibrium constant K. The second equation relates it to something we call reaction enthalpy, delta H, and the reaction entropy, delta S. The third form relates the free Gibbs energy to the redox potential. Now, again, to repeat, delta G, the free Gibbs energy, must be negative, as you can see again in this graph. Now going back to acid and bases, the concept of acid and bases are really old. People are familiar with the sour taste of acids, the bitter taste of bases, and in some cases there is an indicator that indicates acid or bases by a color change. Now these indicators can be some natural products. Reactions of acid and bases in most common form will form salts. Now, there are numerous acid-base definitions and concepts that have been defined and have appeared and also disappeared in the chemical literature. The most simple one would be the one of Arrhenius. We will only touch upon that. But more importantly will be the Brønsted-Lowry acid-base theory and the Lewis acid-base theory. There are many more, but these two are most important to this particular lecture. With reference to all these different acid-base definitions, it's not about which is right, but which is most convenient to use in a particular situation. So actually each approach is correct as far as it goes, and knowledge of the fundamentals is essential. Now, we all have encountered acid-base chemistry in our daily life. One example is depicted here, which you can see in a coffee shop. Have you ever wondered why the color of iced lemon tea is always paler than black tea? Here you can see two depictions. This is a simple black tea, hot probably, and here you add some ice to that and you may add a lemon inside that and you have iced lemon tea. Now you can see also this yellow color is much brighter than that which is almost brown. Now you can ask yourself the question, can this be due to different concentrations? In other words, the addition of ice, which eventually melts to become water, would dilute the tea and therefore dilute the color to become overall paler in appearance. Now, if that's the case, then your Teh O Peng, which is also tea with ice, should also be paler in color, but here you can see it's rather dark. And here again, for comparison, your ice lemon tea. Of course, there is a chemical reaction that has occurred here between the tea and the lemon. So lemon we know is acidic, it has a sour taste, and when you squeeze some lemon juice into a tea, you can see that the color actually changes and becomes paler. Of course, you have a little bit of the lemon also in there, but it only touches the surface of the tea. So here we can observe that tea acts as an indicator to indicate the presence of an acid which is coming from the lemon. Okay, so lemon juice is acidic. Now this slide depicts multiple definitions that appeared and also some have disappeared in the literature. So we have Lavoisier in 1776 who actually defined an acid as oxides of certain main group elements and a base, which is anything that reacts with these acids. As an example, you have SO3 that could react with sodium hydroxide in an acid-base reaction according to Lavoisier. Now the ones depicted in yellow and green and dark green are the ones of concern to this particular lecture. In early times, Arrhenius already defined the Arrhenius acid-base concept, and for him, the proton in water is the acid. And the base is the hydroxide. So an acid-base reaction would basically involve the reaction of a proton with the hydroxide to form water. Examples would be anything that produces protons, for example, sulfuric acid, and the base again is our typical sodium hydroxide. Now this definition is limited to water, so it can only exist in water as a salt. The Brønsted-Lowry definition is an extension of the Arrhenius definition, and an acid is any substance that can actually produce a H+ and acts as a proton donor. The base is the proton ion acceptor, and so we are no longer limited to water, and here the hydronium ion itself can donate a proton, and so it acts as an acid. And the base could be water, and when the water accepts the proton, it will form the hydronium ion. The water can also act as an acid and donates a proton, and when it donates a proton, it will become the hydroxide ion, which can act as a base to receive the proton again to form water. In addition to water as a system, the Brønsted-Lowry definition can also operate in other media. So here we have an example of ammonia acting as a base, which upon gaining of a proton will form the ammonium cation, which of course can donate the proton and be acting as an acid. Now the Lewis definition is even more advanced, and here we no longer consider the proton or the hydrogen ion as the reactive species, but rather we consider everything which contains an electron pair as the base, and everything which can accept an electron pair as the acid. So now we can extend this to metal ions, for example. So silver cation here is deficient in electrons, and so it can accept an electron pair, for example, from ammonia, and therefore ammonia is the Lewis base, and silver plus is your Lewis acid. Now there are more definitions like Ingold-Robinson or the frontier orbital definition, where you have electrophile and nucleophile as equivalents to acid and bases, or you have considerations of the frontier orbitals, which means the LUMO or the HOMO, but these are not of interest to this lecture, and so we will only consider in particular the two ones depicted in light and dark green. You also have more specific definitions like the Lux-Flood and Usanovich definitions. You can look these up on the internet if you wish and basically learn more, but that is up to you. Now let's look at the Brønsted-Lowry acid-base concept. Now while Arrhenius theory only considers the proton as that active species, Brønsted and Lowry, these two gentlemen here, have extended this concept to their own theory. As mentioned already, a Brønsted acid is anything, any substance that can produce a proton. So it donates a proton. Typical example would be HCl, which upon dissociation basically forms a proton H+ and a Cl- anion. Similarly, you have nitric acid and sulfuric acid. So these are the very common mineral acids that we all have encountered before. And typical Brønsted bases are proton acceptors that could be, for example, ammonia or our typical sodium hydroxide. So the Brønsted-Lowry concept expands the Arrhenius theory or the list of acids and bases to include gases as well. So you can have a gas HCl molecule that reacts with an ammonia molecule, and you are actually not limited to water as a medium. So this is just an example, and you can apply the kind of definition to many, many more scenarios. It also introduces the concept of conjugate acids and bases, which is when a species donates a proton, it becomes the conjugate base. In other words, an acid after donation of a proton will become a conjugate base. On the other hand, a species which gains a proton, which is your Brønsted base, becomes the conjugate acid. So this concept is useful, and so conjugate acid and bases are always in equilibrium in solution. In fact, most reactions you can already remember are equilibrium reactions. So here we can see a very generic chemical equation involving acid and base chemistry. So the acid 1 after donation of its proton will become base 1. On the other hand, the base 2 after receiving a proton will become acid 2. The base 2 and the acid 2 is the conjugate acid-base pair, and acid 1 and base 1 is the respective conjugate acid pair as well. Now, substances that can act as both acid and bases are called amphiprotic or amphoteric. Now, water can donate a proton to become a hydroxide ion, or water can receive a proton to become a hydronium ion. So that depends obviously on the reaction partner. When water is treated with a stronger acid like HCl, then obviously the stronger acid now reacts as the proton donor and donates this proton to water, which acts as a base, accepting the proton to become the hydronium ion. And the HCl, after donation of the proton, remains as a chloride. So here you can see the conjugate acid-base pair. HCl is the acid, and it gives rise to the Cl- conjugate base. So water, when it reacts with a stronger base, it can donate protons to that particular base. Here's an example. When water reacts with ammonia, it donates the proton to ammonia, and ammonia forms the ammonium cation, while water forms its conjugate base, which is the hydroxide ion. So again, here you can see the respective conjugate acid-base pairs. Now there are more definitions that we need to consider. Substances that can donate 2 protons are called diprotic, or they are also confusingly called dibasic acid. An example here is sulfuric acid. You can see there are 2 protons that you can donate. After donation of the first proton, of course, you can form the bisulfate, and after donation of the second proton from the bisulfate, you actually form sulfate as the anion. So these are the 2 steps. Step 1, remove of the first proton, and step 2, removal of the second proton from the sulfuric acid. Now the HSO4- anion is called hydrogen sulfate or bisulfate, and the SO4- anion is called sulfate. Now here you can see selected examples of Brønsted acid and bases that react with each other. Now in this case you have hydronium ion that acts as an acid and donates its proton to the nitrite anion to form water and the nitrous acid. Although we depict this here as a simple arrow, you have to remember that all these are equilibrium reactions, and so it's more accurate to actually use an equilibrium arrow here. Now, if we analyze this very simple reaction in terms of all the acids that appear, then we know that the hydronium cation here is the proton donor on the left side. So it is the acid. On the right side, the proton donor would be the nitrous acid. So we have these 2 here as an acid, and their conjugate bases are obviously water, and the nitrous acid, after donation of its proton, will form its conjugate base, which is the nitrite anion. On the other hand, of course, then you have the nitrite anion, which can act as a base to form its conjugate acid, which is the nitrous acid. And water, when it acts as a base, upon accepting of a proton, will form its conjugate acid, which is the hydronium ion. Here you can see water kind of reacting with itself. So you have an hydronium ion reacting with the hydroxide anion to neutralize each other and to form 2 molecules of water. So in this case, water acts as both acid and base. And so you have acid here, a hydronium ion again, or water, and the respective conjugate base is water or the hydroxide. And same treatment here, hydroxide will be the base. Upon receiving a proton, it will form the conjugate acid, which is water, or water acts as a base to form the hydronium ion. So here you can see that water can be an acid, it could be a base, which means it is amphiprotic. Now, if we look at a different example, which does not involve water, then we can look at this typical example, which is liquid ammonia. Now, ammonia is actually a gas at ambient conditions. And so in order to condense it into a liquid, you need to cool it down to at least minus 30 degrees. Now, this is not an ammonia solution in water. This is really pure NH3 that had been condensed down into a liquid. And in this liquid, the ammonia, just like the water itself, can react as an acid or as a base, and so it's also amphiprotic. Now here you can see example of an acid-base reaction occurring in ammonia. So here you have ammonium as an acid that can donate a proton to the amide, and upon receiving the proton, you have formed essentially two molecules of ammonia. So that is the equivalent system, just like in water, but now you operate in ammonia. Of course, then you need to modify the respective chemical species. But again, if you analyze the whole thing, you have ammonia here acting as an acid to become the conjugate base ammonia, or ammonia as the acid, and upon deprotonation, it becomes the amide anion. Or ammonia can act as a base, receives a proton to form the conjugate acid, which is ammonia, or the amide is a very strong base and receives a proton to form ammonia. So here you can see again ammonia appearing as an acid and as a base. So ammonia is both, again, Brønsted acid and a Brønsted base in this particular scenario. And it is also, just like water, amphiprotic. Now here we will look at more examples of Brønsted acids. You have very typical hydrogen halides. So we have seen HCl already, but you can also have HF, HBr, or HI. These are usually very strong acids, and you can generalize them as HX, whereby the X stands for an anion, which is the halide. You have particular acids that contain oxygen, and these are called oxoacids. And one example we have encountered already, which is the nitric acid. And we have also seen the nitrous acid already. Then we can have perchloric acid, and sulfuric acid is also something that we have seen already. Phosphoric acid is another very famous example, and you can see here phosphoric acid can potentially donate 3 protons, so it's actually a tribasic acid if you wish. Here are the Lewis structures of the respective acids: nitric acid, nitrous acid, perchloric acid, and here you can see the acidic proton here depicted in red. And so these 3 acids can donate 1 proton each, right? And so they are called monobasic acids. Here you have sulfuric acid, the Lewis structure depicted here. It can remove 2 protons or donate 2 protons, so it's a dibasic acid. And the phosphoric acid can donate 3 protons. Again, it acts as a tribasic acid. Now what you can see here in all of these oxo acid is an oxygen which has a double bond to the central element. So that is the essential requirement for something to be called an oxoacid. The other oxygen, which contains a single bond, usually carries the hydrogen atom to be donated. Here we can see a few examples of inorganic Brønsted bases. Very typical would be sodium hydroxide, potassium hydroxide, lithium hydroxide, ammonium hydroxide. So the important thing here is always the hydroxide. So these 3 basically involves alkali metals. This one has a different cation, right? It is an ammonium cation, but essentially they are all hydroxides. You have nitrogen bases like the ammonia molecule, and the ammonia molecule can be deprotonated to form an even stronger base, which is the amide. So you have sodium amide or different alkali amides like potassium or lithium amide as depicted here as well. So these are called the amides. Now we have also organic bases, and they can be simply derived from ammonia by replacing 1 proton each with an alkyl group, so you have replacement of one proton with one alkyl group, that would give rise to a primary amine. If you replace two hydrogen with an R group, then you have secondary amines, and if you replace all three with an R group, then you have a so-called tertiary amine. Now all of these amines are organic bases, and the R would stand, as I mentioned already, as an alkyl group, or it could be also an aromatic group, but in most common cases, these would be simple alkyl like methyl or ethyl and so on. And they give rise to a large library of organic bases. Now, we can consider how strong acid and bases are. And so when we talk about acid strength and base strength, usually what comes to mind is the pH scale. Because the pH scale is something which we all are aware of. And so you can measure the pH of a solution. And what we define here is as long as the pH value is below 7, we can call it acidic. When it's above 7, then it's alkaline. And when it's 7, then it's neutral. Now you have all encountered all this already. So you have these aqueous solutions with different types of acid and bases. And at the same time, there's also an indicator that basically through color changes indicate the pH state. Now the question is, of course, what is actually the pH value? The pH is defined as the negative logarithm of the hydronium ion concentration. When you encounter P, is always having to do with a negative logarithm of something. Now, the hydronium ion is the H3O+. You can simplify that by replacing it with a simple proton, right? So the simplified form would be pH equals the negative log of the proton concentration. So concentration is something that we put in square bracket here. And so the pH actually is reflective of a concentration of protons in a solution. It is not necessarily a measure for acid-base strength. For example, a given acid could exist in different concentrations and therefore giving rise to different pH values, although it's actually the same acid. Now here you can see also typical examples of substances that would have typical pH values. If you measure the pH of hydrochloric acid, a specific concentration mentioned, you can get an even negative pH, so which means it's pretty acidic. More common, you have gastric acid. This is what you have in your stomach, and that is assisting us in digesting our food. Vinegar, you know, is also acidic, and milk is slightly acidic. And on the other hand, soaps obviously are alkaline, and coffee and beer is also slightly acidic. Now, when the pH is not really a measure for the acid strength, then what is? Now, the strength of a Brønsted acid is measured by its acid constant. And we mentioned already that acid-base reactions are equilibrium reactions, as most of the reactions are. And for each reaction, you can actually formulate an equilibrium constant. So here we have a typical acid, HA, in water. That means it's aqueous. And so that acid in water acts as an acid to protonate the water to give rise to a hydronium ion, which is again surrounded by water, and that is indicated by AQ. And it will form its conjugate acid, which is simply the A-N ion. Now, this is a reaction that can occur in both directions, and obviously the position of the equilibrium is dependent on how strong my acid is. But in all these cases, I have an equilibrium constant K, and A indicates that we are talking about an acid equilibrium at this particular moment. Now, the equilibrium constant Ka is defined as the concentration of the hydronium ion, which means the concentration on the right side multiplied by each other. So the hydronium ion concentration multiplied by the A- concentration. And that needs to be divided by the left side. So we have the concentration of the initial acid multiplied by the concentration of water. Of course, when we work in water, then we have a lot of water around. And so we can actually incorporate the concentration of water into the Ka by simply equalizing it to 1. So that would give us the simplified version of Ka, which is essentially the product of the hydronium concentration and the conjugate base concentration divided by the concentration of the initial acid. So you have, for a strong acid, a very large Ka, because the concentration of the hydronium and the conjugate base will be very large, whereas the concentration of the acid is very small because it reacts to form the right side. So again, for a very strong acid, we have a very large Ka value. So the same treatment of bases. So a base here can receive a proton from water to form its conjugate acid and the hydroxide ion. And Kb would be the equilibrium constant for this base reaction. And so Kb can be treated in the same way, the products of the concentration of the products divided by the concentration of the starting materials. And again, you can equalize the water concentration to 1 and you get a simpler version of Kb. And again, the larger Kb, the stronger is my base. And of course, you can form the pKb. And again, remember, whenever you encounter P, that means you have a negative log of something. And Kb is the one that you need to do this negative logarithm with. And so you obtained pKb. Now for water, we have something which is called autoprotolysis. Because water, as we know, is amphiprotic. It can react as an acid and also as a base. So you have a proton transfer equilibrium that exists even in the absence of any added acid or bases. So this process is called the autoprotolysis. It always occurs, but not very significant, right? But it still does occur. And so for autoprotolysis of water, you can formulate this reaction scheme here. Two equivalents of water, one acting as an acid, one as a base, will form, therefore, a hydronium ion and a hydroxide ion. And so this is the equilibrium that occurs in water, always, even without addition of any external substances. And so the equilibrium constant for this particular reaction is Kw, and W stands for water. And so Kw can be defined in a similar way as Ka or Kb. You take the product of these concentrations and you divide it by the concentrations of the starting materials, which is water in this case. And of course, you would have to consider this stoichiometry, the 2 here, as an exponent. But it doesn't really matter because we can equalize the concentration of water to 1. And so the Kw is essentially the product of these two factors here. And we can tell already that this is the value for Kw. And if you form the pKw, of course, then you have 14 here because you would take a negative logarithm of this particular value. Now to summarize, the strength of Brønsted acid and bases is determined by the equilibrium constant, or the pK. And here we can also define that the Kw is the product of the Ka times the Kb. That's a definition that you can remember. The pKw is the negative logarithm of the equilibrium constant of the autoprotolysis, Kw. pKa is the negative log of the Ka, and pKb is the negative log of the Kb. And the sum of the pKa and pKb must give rise to 14, which is pKw. So the larger the value of Ka, as mentioned, the stronger is the acid. The smaller the value of pKa, then the stronger the acid. Okay, so do not forget again that the P stands for a negative logarithm. So the larger the value for Kb, the stronger is the base. And again, the smaller the value of pKb, the stronger the base. So here we can see examples of a strong and weak acid and bases. Depicted here is the conjugate base as well, which means typically the anion of the particular acid. And here you can see the comparison of the different pKa. Hydroiodic acid has a pKa of -11, so it's an extremely strong acid. Other strong acids would be perchloric acid, hydrobromic acid, HCl, and sulfuric acid. They all have negative pKa. Here we have the moderately strong acids, right, or weak acids. They have positive pKa. And so again, pKa of less than 1 indicates a strong acid, and they are usually fully deprotonated, which means fully dissociated into a proton and the anion in aqueous solution. And if you have pKa greater than 1, these are weak acids. And so you have equilibrium state here, proton transfer equilibrium lies in favor of a non-ionized acid. This is the final slide for this lecture. And here you can see even weaker acids. For example, the pyridinium ion, which is the conjugate acid of pyridine, has a pKa value of only 5.25. So that makes it a rather weak acid. There are several other examples of very weak acids, and some of them have even a large pKa of 19. And remember, the smaller the pKa, the stronger the acid. So this is a rather weak acid. Finally, a strong base is a species that is almost fully protonated in water. As an example, you have oxide anion, O2-, and so when you dissolve an oxide in water, it will be immediately converted by protonation into the hydroxide ion. And even the hydroxide ion is a pretty strong base and could be further be protonated to give water. On the other hand, a weak base is only partially protonated, so there is a greater equilibrium between the ammonia and its conjugate acid, the ammonium, as depicted here. So ammonia is a moderately strong base, and it gives rise to a moderately strong acid. In general, a stronger the base, the weaker will be its conjugate acid. And conversely, the stronger the acid, the weaker will be its conjugate base. So that is the end for this lecture. And just to recap, today we have learned about the Brønsted-Lowry acid-base theory. And a Brønsted acid is a proton donor, whereas a Brønsted base is the proton acceptor. And within this definition, you have the respective conjugate acid-base pair. We have learned that these acid-base reactions are in equilibrium. You can formulate an equilibrium constant. And the larger the K, the stronger the respective species, whether you're looking at an acid or as a base. All right, so this concludes this lecture.